Rust exposes all the details, so at first everything may seem confusing, but I'm going to help settle the confusion in this video all about strings. The topics of what we cover below, you might also find that in the description too with timestamps, so you can quickly skip to what's interesting for you. So what is a string? A string is a sequence of characters to represent text, but computer memory doesn't know strings, it only knows ones and zeros. So to look closer like memory, our string can be thought of as an array of characters. But actually, instead of characters, we could map each character to a number. Or how about instead of a base 10 number, we do a base 2 binary number. Now we have binary that can be put into memory. We just transformed, more specifically encoded from a string to a binary form of the string. Problem? There are so many different ways to do this transformation. Like how do we get the number of the character in the first place? That's why Rust has different string types and why we have to be super careful when sharing strings between languages. Or strings might look like this, it's called mojibake. Let me address two challenges of a string in binary that every software seems to do differently. We have to support both directions to and from binary. For now, think we're in binary and we want to decode to a string. First, how to decode a single character. Fixed size characters would be simple to decode. Every 7 bits could be a new character, but it limits us to 128 characters. Or we could use 32 bits to represent a character. We'd get heaps of characters, but more memory would be wasted. Or idea? We could vary the bits, so more common English characters use less bits, and less common characters such as an emoji would use more bits. Whatever you do should be defined clearly. That's why we have character encoding standards. More on that in a moment. The other challenge when decoding a string. How to know when to stop reading the binary. When are there no characters left to decode? We don't want to accidentally read memory that isn't ours. Typically 2 approaches. More common today, storing a length so your decoding function knows how much to decode, or having a pattern in binary to represent the end, which only exists at the end, also known as a null character. Now we know the basics how a string is represented in binary. Let me explain more about character encoding. A greeting face in Unicode is 128,512. The standard way to encode decimals is to divide by 2, record the remainder, blah blah. In summary, in binary, 1 looks like a 1, 2 looks like 1, 0, until 128,512. This number in base 10 would look like this in binary, base 2. But character encoding standards redefine how a decimal is converted to binary. So forget all that classic knowledge learned in school. Look at an array of memory. If we did the encoding to binary the old school way, each character would have to be a fixed width, so we know when to start decoding each character. 32 bits for each character means about 4 million characters. But 99% of the time, at least in English, we're using about the same 100 characters. So 32 bits is overkill and would use more memory than necessary. But any less, I wouldn't be able to use my emoji. So that's why we have different encoding standards to allow us to use any character we want without totally wasting memory. Today in 2026, there are about 159,000 characters defined by Unicode, but it supports over 1 million. Characters are being added all the time. Unicode defines how each character maps to a number, but doesn't define how each number maps to binary. That's what the other standards such as UTF-8 define. The char type encodes a Unicode value to binary the classic normal way we encode numbers to binary. So we get this. UTF-8 is the dominant popular character encoding standard. It defines its own way to encode a Unicode value to binary. The string type guarantees UTF-8, so we get this different binary value than above. UTF-16 would also have its own different algorithm too, but Rust doesn't have a library type that guarantees UTF-16. UTF-8 and UTF-16 supports all characters of Unicode. UTF-16 is more efficient for languages like Chinese, Japanese, and Korean. Another character encoding standard, ASCII, only supports the first 128 characters of Unicode, so it doesn't support our emoji at all. Let me show you the benefit of UTF-8. Let's take any letter from the English alphabet and UTF-8 will encode this to an 8-bit value. But let's try an emoji, and we can see this is 32 bits. This variable length encoding is what makes UTF-8 so useful. Common letters take less space, but we still have support of all the other characters of Unicode if necessary. Remember, Unicode defines each character to map to some number, and the specialized encodings define how each Unicode number is mapped to binary. So far, the concepts I've explained are quite general for any software, but let's focus on Rust for a bit. How to create a string, a basic common string for 99% of use cases. There are a bunch of ways to get that object, but none of them include literally assigning a string to the string, because Rust automatically assumes this is a read-only static str that you refer to, not a string object. For something basic, I would suggest adding .toString because it expresses intent quite clearly. You might find alternatives such as into, toOwn, string from, and there's probably more. The other option, if you have values you want to put in the string, you can use the format macro, which allows you to construct a string object with arguments in a nicely formatted way. Now back to more theory. What's the difference between a string and a str? A str, also called a string slice, is an array of valid UTF-8 characters. Since you see the ampersand, this is technically a reference to the array. It's comparable to a U8 slice, almost the same as above, but without the guarantee of UTF-8 characters. And a string? It's just a wrapper around a vector.
It contains all sorts of methods you want to do to a string, with the guarantee the underlying data always consists of UTF-8 characters. To get the reference to the actual underlying data, we call OsString. This is a VEC-U8, which is a struct containing a pointer, length, and capacity. It's a type that manages the heap, and to view the underlying data we call OsSlice. And this slice is ultimately quite similar to a reference to a str, just no guarantee the data only contains UTF-8 characters.
Why so complicated? Things are complicated because we're dealing with the heap and Rust is exposing all the details for us. Str is the actual string type, and string is like a container for str. In other words, we're using known fixed sized objects on the stack to manage unsized dynamic objects on the heap. It's not as simple as making a, for example, U32, which has a fixed size of 32 bits or 4 bytes. We can't do let a str equals something because Rust will say that all local variables must have a statically known size, which is because every function must know how much of the stack it allocates when called. Rust is also 2 steps ahead and made this read-only memory that can be referred to. So we can make this a reference to a str instead and the compiler will be happy. But if we want this on the heap, or rather to dynamically create the string, we can create the str directly in a box, which is like a unique pointer from C++. That's a bit unusual. Normally we'd just use the string type and it would do something like that for us. And then we'd also get useful methods such as push str. So now you know why we have string and str types. What's the CString type in Rust? It's an alternative to string. Instead of guaranteeing valid UTF-8 data, it guarantees a C-compatible string. That means in the binary form of this string, there's a sequence that represents the string is over, which is known as the null character. A C-string doesn't depend on a length, just this null character that it's at the end. Rust has this type to be useful when interrupting with other languages such as C. Example, we can make a function that will be called by the C language which will return a C string. There's no need to return the length because the user can figure it out on their own. Warning, be super careful when doing stuff like this. It's very easy to make a mistake such as causing undefined behavior or memory leaks. And that's a brief explanation why we have the CString type. Now onto the next type, OsString. It represents strings the same way as the operating system where the code is running. Different OSs natively support different types of character encoding. Where this is important for most of us is when dealing with OS level API calls, such as file system or native user interfaces. On Windows, strings are often sequences of non-zero 16-bit values, so we can get a string like this when we want to call some interesting Windows specific function. But on Unix, strings are often sequences of non-zero 8-bit values, often interpreted as UTF-8. And if everyone did it the Rust way, strings would be valid UTF-8, which may contain zeros. We can get the Rust string, like so. Getting the native strings for the respective OS, like we did above, is done with little to no overhead because the internal representation of the OS string is very platform specific to match the OS. That's the power of OsString. We use this type to minimize platform specific code in our codebase. Oh, and there's also the type OsStr, which is basically a slice. Just how we have str for the string type, we have OsStr for the OsString type. Rust doesn't support overloaded functions, meaning same name, different arguments. Or can it? A function can accept impl as ref str as an argument. That means users have an easier time calling the function. They can pass in a string literal or the string object, or well, anything that implements the asref str trait. And the function can use it like this by calling the asref method. Alternative approach is to accept the string object or a reference to the str, but now the caller has to pass in the exact right object just to keep the compiler happy. You could also accept a reference to a string. No, please don't do this. You're forcing the user to have a string object when you don't even take the ownership.
Rapid escape saved.
There's no benefit for the function itself nor any caller to take a reference of the string. Back to the main topic, I'd suggest only using impl asref str when you want an actual reference. When you want to take ownership, take in the string object. Otherwise, you're at risk of causing more allocations than necessary. Because for example, the user might see this as an argument, create their own string, then inside of the function, we create another string. No big deal, but a tiny bit more work for the computer than necessary if the compiler didn't optimize it out. So that's it. I think it's pretty cool how we can achieve something like overloaded functions without technically being overloaded functions, just with traits like this. That's it. I filmed this video over the course of a few weeks, every evening after work. By the way, this is kind of funny. My roof is kind of flooding from the neighbor above, so I'm trying to deal with that at the moment, and hopefully it's fixed soon. But anyways, thanks for watching the video. Hopefully you found some value in it. If you have any suggestions for the future, please let me know. Please subscribe, and see ya.